Now we're going to do an example. We're going to try to find the pressure required to pump oil through a 35 centimeter diameter pipe that is 250 meters long at a flow rate of 0.4 meters cubed per second. The epsilon of the pipe, the roughness of the pipe material, is 0.05 millimeters. The density of the oil is 950 kilograms per meter cubed. The viscosity, the kinematic viscosity of the oil is 2 times 10 to the minus 5 meters squared per second. So let's see how we do this. The first question we have to figure out is this a laminar or a turbulent flow? Now you're given a surface roughness, so you might be, oh, it's going to be turbulent because I give a surface roughness, or Professor Fowler could just be messing with you. So let's figure out if it's laminar or turbulent. How are we going to check that? Well, we check that with the Reynolds number. We know that the Reynolds number for turbulence, the transition occurs at 2,000 of the Reynolds number based on D. So we need the Reynolds number based on the diameter of the pipe. That's the average flow velocity times the diameter of the pipe divided by that viscosity. The average flow velocity we can find based on this flow rate. So we have a flow rate of 0.4 meters cubed per second. What kind of flow rate is that? Well, it is a volume per second flow rate. Meters cubed is volume, so that is a volumetric flow rate. We know that volumetric flow rate, Q dot, is equal to the average velocity times the cross-sectional area, so the area of the pipe. So I can solve that for you, the average velocity, which is equal, therefore, to the Q dot divided by the area of the pipe. The area of the pipe, remembering to use the diameter, use the radius of the pipe, pi r squared, comes out to be 0.0962 meters squared. And the Q dot, of course, is already given to us as 0.4 meters cubed per second, which means my average velocity is 0.4 meters cubed per second divided by that area, 0.0962 meters squared, which gives me 4.15 meters per second. So I've got a flow rate of average flow velocity of 4.15 meters per second. I'm going to plug that into my Reynolds number based on D. 4.15 meters per second. My D is 0.35 meters, 35 centimeters, and my viscosity 2 times 10 to the minus 5th meters squared per second. So I crunch that into my calculator. I get 72,756. So that is solidly turbulent. That is well above 2,000. I have 72,000. So I am well into the turbulent regime. To find the pressure drop, therefore, I have to use the friction factor. Friction factor formula for pressure drop, delta P equals F times L over D times the average velocity squared divided by 2 times rho. So I know L, I know D, I know average velocity, I know rho. The only thing I do not know is the friction factor. So I need F. How am I going to find F? Well, I'm going to probably use the Moody diagram. But in order to use the Moody diagram, I need two things. To use Moody, I need the Reynolds number based on D. Well, I just calculated that. That was 72,000, so that's all right. And I also need the epsilon over D. So in this case, the epsilon over D, I had 0.05 millimeters, and D was 35 centimeters. So I got to be careful here. I got 0.35 meters. So I got to make sure those are, I got to line up my units here. Or I could use centimeters. But at any rate, if you correct your units, you get 1.4 times 10 to the minus 4 for my epsilon over D. So that's my epsilon over D. Now I go to the Moody diagram. I'll pull it up here. Should have left it open. Apologize for the delay. Thumbing through my book. This is going great. There we go. I'm almost there. All right, here's my Moody diagram. Boom. Now, I'll zoom in again for you. We'll try to read it together, though, because that's going to be kind of hard. So my epsilon over D, I said was 1 times 10 to the minus 4. So that's going to be this guy right here. 1 times 10 to the minus 4, roughly 1 times 10 to the minus 4. That's going to be this line. And then I'm going to come out here to 70,000. So 70,000 is, this is 10,000, this is 70,000. Up to that line. Goes right about here. I'm going to come across, looks like it's 0. Actually, all right, 70,000, is that right? Oh no, I'm sorry, I was at 700,000. 70,000's here. Here's 20,000. Here's 70,000. Coming up to this line again, I get about 0.2. So 70,000 right here, 7 times 10 to the fourth. Coming across to this line here, 0.001 line. That gives me about 0.02 off this Moody diagram. All right, so F from the Moody diagram, 0.02. So then I plug that into my equation here. So here's my equation. Sorry, I'm going to zoom back out. There's my equation, 0.02. So the pressure drop, 0.02 times L, which is 250 meters, I think we said. Then we have 0.35 meters for the diameter. And we have the average velocity, 4.15 meters per second over 2. This is squared, so that was not great. That should have been squared. Hopefully I had that squared in the earlier formula. And you caught it. Hopefully you all thought, oh, wow, he should have put squared for that. So anyway, that's squared. And yeah, I did have it squared before. So that's squared. So I have 4.15 squared, and then we multiply by rho, which we said was 950 kilograms per meter cubed. All right, so there's my formula. I plug that all into my calculator. I get 81,807 divided by 0.7, and that's equal to 116,867. Got way too many sig figs there, but anyway, is what it is. That's your pressure drop in that pipe to achieve that flow rate using the friction factor, which we get off the Moody diagram, for which we needed this epsilon over D, and the Reynolds number, which we calculated was about 72,000.